Hi everyone, so today we are officially going to do our frequency lab for Engineering 110. So you're all masters of, at least theoretically, of discrete Fourier transforms, so now it's time to actually put it in action. So unfortunately I'm in my office right now, again, so we can't do this in person, but at least you can kind of understand how the experiment was performed so that when you do the data analysis, things should actually kind of come into play. So what we're going to be using is our old friend, our vernier sensor DAC. So we're going to use that data acquisition device, the National Instruments, in order to acquire our data. We're going to use our aluminum beam, which is Al-6061. We'll do some measurements of some very important dimensions in a second. And then we have our accelerometer. So this is our vernier low G 1D accelerometer. So in that direction, that's where we're going to measure the acceleration and then convert that into frequency space and time space, or that time space into reciprocal space, which is frequency space. We have our C-clamp and some power cords and some other good stuff, and that is just all my pens. I wish I could just write that, or maybe you don't, maybe prefer my stylus handwriting, but I wish I could give a lecture like that again. And we're going to use, again, our tool, which is LabVIEW, but again, our data analysis tool is really going to be Mathematica, and you're all experts in Mathematica as well at this point. But remember, we're going to put our front panel, just like in the last video for over here. Sorry for any kind of screen, again, view. And we're going to put our back panel, which is our block diagram, the guts, essentially, of our diagram here. So let's go ahead, and we're going to start to kind of assemble this. So all we're going to do is, well, first, let's go ahead and measure some dimensions of our aluminum beam. So let's try to zoom in here. So when I take measurements of the base, it looks around like 25 millimeters. If I do the height, which is the thickness of our beam, let's see if I can get in here. Oops, let me go into this direction. Let's see if you can see. But you see it's about 3 millimeters, just like I said in the lab handout. And so now we're going to kind of connect everything else. So that's kind of a laborious part, and I can't do that while holding a video camera. So I'm going to do that, and then we're going to come back. All right, I'll see you all in a second. Thanks. And we're back. So you can see I've attached my aluminum beam to my desk with the C-clamp. I have it extending like in a cantilever beam fashion. Although, again, what are the assumptions for cantilever beam? Massless, rigid, and basically there's no mass here at the end. So we're going to see how our results might differ from the theory in a second. But I've got my C-clamp, aluminum beam, and you can see right here my low G accelerometer pointing in the direction where we're going to experience vibration. And when we get vibrations, we are going to do discrete Fourier transforms. So I'll get my ruler out here in a little bit. Again, my accelerometer here is attached to the first channel of my DAC. My DAC is connected to my computer. And so now let's go ahead and build our block diagram. All right, we are back, and we just finished doing our block diagram in our kind of other mode of recording. So again, we still have the same kind of components here. So what I've done here for this particular lab, we are going to set my sampling rate. You can see here, 150 samples per second, 2 seconds. And let's make sure that we don't have, hopefully, aliasing or spectral leakage here. So let's go ahead and run this experiment. So I'm going to press OK. It's going to take some time to think about it. All right. So what's going to happen here is I'm going to press play with one hand, and I'm going to add a deflection here. So let's look at the deflection first, and then we could look at and see the output on our graph over here once we're done. So I'm going to press play, and then I'm going to quickly switch hand or deflect our beam. So deflect it. Oops. Let's do that one more time. All right, take 2. Actually, it doesn't really matter, but let's go ahead and get us set up again. So I'm going to press play, and I'm going to deflect our beam. So let me do that. And you see it doesn't really need too much of a consideration. So this is showing the first run and the second run. So let's actually look at the data set that we gathered. So we have a 35 centimeter length beam. So let's go ahead and figure out, or actually try to analyze this data. So here's my frequency, I've got my inertia, there's my equation for F. I know F, I'm going to replace slash dot. H goes to, where's my H? I was so nice in this notebook, giving all those values, although it's unfortunately, again, you can't actually measure yourself. So 3 millimeters, so 3 times 10 to the minus 3. My Young's modulus is going to be 69 gigapascals, 10 times 10 to the 9. My rho is going to be equal to 271,000, 2710, I think so. 2710 in kilograms per meter cubed. What else do I need here? And the length of the beam is 35 minus 2. So let's look at that numerically. So looking at this value, we should expect to measure a frequency of about 20 hertz. Now, we measured what was our sampling frequency? It was 150 samples per second, so 150 hertz. So we're well above, we're not going to be aliased here. So let's go ahead and analyze this data. So I'm going to look and see. Actually, I'm going to import it the old-fashioned way. Just look at this raw data. This is going to be a little different from your data set because it was super nice and analyzed, or actually kind of removed a lot of the junk that you can see here. So I'm going to grab this from 23 to -1. And here's my time data. Here's my other data as well, our acceleration data. So I'm going to call that my DAT. I'm going to plot my DAT here. Excellent, looks like our curve. So you can plot it as this line plot too. Not as exciting, not as cool. So our time DAT is this. So we can see our delta T. Again, a little bit different, but again, the reality of actually running the experiment. So our DAC has a hard time to kind of keep up with that high sampling rate. So it's going to be a little bit different. That's why it's, again, very important for you to check your data set and see if you're really aliased. So there's your big N, your T, again, 2 seconds, but not really 2 seconds. So now let's calculate our DFT. So this is all our acceleration data. So we could do our A sub N, our B sub N's. And we're getting rid of that here. And let's go ahead. Let's see, figure out for 35 centimeters. So it's around 12. So again, why would it be a little bit lower? Actually, you see it look a little bit of a different frequency here. Why would it be a little bit lower for that 35 centimeter beam? Actually, was it 35 or 30? Actually, 35 is the. Why would it be a little bit lower? Well, what are our cantilever beam assumptions? We assume that it's rigid, not rigid. We assume also it's massless. It's definitely not massless. Instead, there's actually this additional mass that's on the end of that beam. So it's going to be harder. It's not going to, basically resonate as freely because there's this additional mass at the end of it. So that could definitely cause that difference. But you need to see if our uncertainties overlap. If the uncertainties overlap, right now they look so different, right? But let's see if those uncertainties overlap to see if they're structurally distinct. And let's see how this data is going to look like for our next measurement. All right, thanks, and I'll see you in the next video. All right. So we ran and we analyzed the data that we have for our 35 centimeter length beam. But now what I want to do is I'm going to shorten the length of this beam, and we're going to run another experiment, and we're going to see how the results differ. So now we have a shorter beam that's 32 centimeters in length. But we're going to repeat the same experiment, so same sampling frequency. So let me get my run over here. So it's going to run until we do 2 seconds. So I'm going to, again, click, deflect it, and then we're going to get to go. And you see, again, we record for 2 seconds, and now we're going to get into our data analysis. Now let's see the size, or let's measure the frequency of our beam for the length of 32 centimeters. So as we decrease for length, we see that the vibrational frequency increases from 19 to 23. So let's go ahead and see what our experimental results tell us. So let's go into our video, 32 centimeters length. Let's paste that in just like we did previously. Once you have your data in the correct format, you can deal with these data sets quite easily. So we're just going to run through these again. Time data, again, slight differences because our DAC has a hard time keeping up with the data. We have some new acceleration values, new harmonic coefficients, and we'll see a shift in this data now. So you can see now our frequencies around 15. So again, still lower. Why? Because we have that mass at the end of our beam. So let's go ahead and see what happens for our last measurement. So now we have a 15.5 centimeter length beam. So we're going to do the same sampling rate, 150, same experiment, and then we're going to analyze the data and see if we see something different. So let me do our usual click, flag together, and you can kind of see the difference here. And now we're going to go into that analysis and see if we see something very interesting. So now we're dealing with 13.5 centimeter beam, and now our frequency is 100. What's the problem here? Well, we know that we've been sampling 150 hertz. So we know the rule to avoid signal aliasing is we need to be twice that. So if we're trying to measure a signal of 100 hertz, we need to be at least greater than 200 hertz for sampling rate. So we've aliased our signal. So let's figure out, let's see if we can kind of see that in our data. See if we see a big difference. So let's look here. This is my acceleration data, time data. You can see still very similar, small differences because our DAC has a little bit of trouble keeping up. And now we can look at our harmonic coefficients, and let's look at our curve. So very, very kind of different looking curve, but look at the difference here. 47, almost twice. Again, this is going to be very, very different, ostensibly from our kind of data that we're going to see here. So, but the key point is, if I'm trying to measure a signal that has 100 hertz, I need a sample greater than twice that, so more than 200 hertz. So with that is the end of your lab. So I'll see you in the strain gauge lab. Thanks. Bye.